Hello, this is it, the very last talk. Unfortunately, everything needs to end someday, sometime, and now we are ending and closing Dotnetos Conference with the very last talk, which will be about migrating to .NET to .NET, .NET framework to .NET. As the very last talk, I also want once again thank you, our sponsors, because it is because of them that we are here today. So thank you, Allegro Pay, for giving us support in doing this conference, and also thank you, Demand, for doing the same. You are awesome, and we appreciate your help a lot. And also, we wanted to say that till the end of today, you have this coupon that you can use as a discount for buying our courses just for the end of today. And big thank you for everything and everyone who was attending. And without further ado, because we have still the very last speaker today, let's give the scene to Krzysztof, and with his talk, The Road to .NET. Hello, Krzysiek.
Hi, everybody. Today's talk, I will be talking about the project I've been a part of for the last year and a half. This was a migration from .NET Framework and Windows Server to .NET 5, .NET 6, and then Linux, and the lessons we've learned migrating, the epic failures we had, and how we fixed them. So, firstly, shortly about myself, I graduated from Warsaw University of Technology. Shortly after that, I moved to Seattle to work for Microsoft, where I worked on Windows Phone and Windows 10. Moved back to Warsaw, where I now work in Adform. Adform is a ad tech company, which means that we deliver ads on the internet. Basically, we do real time bidding, so systems that handle a lot of traffic requests and are real time, so very low latency. And this migration story is about one of our systems, so also a high load system, also a system that handles a lot of requests and needs to handle them fast. So this is basically a very short description of the service that we were migrating, starting on .NET Framework, as mentioned, IIS, Windows Server. The system was designed to handle 40,000 requests per second. At the time of starting this project, it was already handling like a couple times that, so hundreds of thousands of requests per second. And there was a big need to scale it. So that's why we invested into migrating. That's why .NET 6, 5, 6, and the expectation was to migrate it not only to .NET 6, but also to Linux, so CentOS servers. We were expecting like 3 or 4 times the traffic. So there was a time constraint, basically. Service was getting more popular. We needed to act fast. And obviously, we still needed to keep the initial SLA of like responding in milliseconds. So like give or take below 200 milliseconds for a response, which is relatively low and not an easy thing to do. So a high level architecture of the service itself. It's not super complicated. It's basically a API behind the load balancer that talks to a bunch of stuff, mostly to one other API also behind the load balancer. So there's a lot of HTTP calls coming and going, but also has like some SQL integration, a bunch of external caches, bunch of internal ones too. But the external ones are the troublemakers. We've got some APIs, and we also write to Kafka. The big parts of it are shown here with the black arrows. So the one external API, one cache, and Kafka are our biggest integrations. The rest is more of a smaller one, like a background one, not on the hot path. And maybe a word on why we migrating. So .NET Framework is going away, being deprecated, not being developed, whatever you want to call that. .NET 5, 6, now 7 has a lot of performance gains and improvements, which are really nice, and we've enjoyed them on other services. What I mentioned before, like we had actually like problems scaling the system. So because it was designed for a lot less traffic than it's handling right now, so we were doing basically horizontal scaling by throwing more machines at it and hoping that it will be enough, which is costly and not very optimal. So yes, hardware utilization, vertical scaling, those are like big problems for us. So we couldn't really use bigger machines very well. Like throwing more like CPU cores at the problem didn't solve it. We had to actually resolve to using more outdated servers, which were weaker. And we also had like problems with connection stability, lots of different ones. So that's why we wanted to migrate. Adform runs a lot of things on Linux, so unification of OSs in production was also one of the reasons. And we also have previous successes. This is not the first system that we migrate from Windows to Linux, from .NET Framework to .NET Core, now .NET 6. And this is not even the biggest service that we've migrated. Like the previous one was handling like millions of requests per second. And it was a success. So we thought, okay, we got this. We've done it before. It's going to be easy. We were very hopeful. One word of caution, maybe, before I start, that this is not a benchmark on OSs. I'm not like recommending anything here. I'm not saying one is better than the other, or like one that Linux is better than Windows or anything like that. Like this is just like we had our reasons. Other people may have other ones. So yeah, let's keep it in mind. All right. No migration can happen without like some actual code migration. So this is the boring part, but unfortunately had to happen. So basically, like .NET Framework, we used IIS, which had like HTTP context. Kestrel has a different one. There was some creeping of the context into application code in our case, so we had to like refactor a bunch of stuff. We took the liberty of refactoring even more to make sure that we improve the code quality as we migrate. We don't like hack it and just make like workarounds and ugly hacks. So we took our time here before actually like going to production. We besides adding a bunch of unit tests and integration tests and end-to-end tests, we also run OpenDiffy, which is a nice tool that allows you to compare outputs from your services. So you basically mirror the traffic and compare the candidate version to the control version and see the outputs. This way we actually found some smaller issues and we were able to fix them before they hit production, which was really nice. And yeah, that's all about refactoring. This is a performance conference, so we're gonna be talking about that. This is our first try. So this is at the point where the code was already building on Linux. We were able to deploy it. It was passing all the tests. It passed Diffie tests, and this is basically the first steps on production. The yellow line is Windows. The blue line is green line is Linux. So it's already faster. The graph is showing CPU to request ratio. So basically, how much CPU does it take to handle whatever number of requests. And it shows that it's faster from the get-go. It's not a lot faster, like probably less than 10% over here, but still, like for the first try, it's pretty good. You can see some like worrisome spikes every now and then that it's getting slower, which is worrisome. But again, like this is the first try, like what you're gonna expect. So one thing that we noticed like right away is that our CPU cores are not being used properly. So we had actually two different issues with this. On the left side, you can see that's basically half of the cores were hot and handling traffic, and half of them were cold and not doing much. And the right graph is a pretty rainbow. which was also fun to discover. Both of them have different reasons, and the reasons are listed here mostly. So we basically checked a bunch of hardware settings, BIOS, tuned profile. Kernel version is the one that caused the pretty rainbow. For some reason, we were running on like a very outdated kernel, and the cores, the CPU was behaving strangely. NUMA node setting also affected it. We had issues with different number of CPU socket count on VMs. So same VM, but with 2 CPU sockets instead of one would give us like one of those. So basically like half of the cores were not working as much, which was strange, but an easy fix. And one thing like nice to note here is that .NET does have like some settings that should be enabled here, like the server GC, obviously, threadpool and GC settings to allow it to use all CPU groups. So first issue solved. Happy about that. And at this point, it was looking way better now. More than 10% faster than Linux without any actual code modification. So basically, both of them are running the same code. We didn't need to make any fixes yet. All we fixed was machine configuration. So nice. But again, we noticed something weird, something that didn't happen on Windows for whatever reason. But we noticed that a lot of our TCP connections were getting into the time wait state, which is not ideal. So time wait is basically a regular TCP connection behavior. It's meant to catch delayed packets. It has a configurable timeout. So basically, after closing the connection, it will stay in a time wait state, allowing for delayed packets to come, not to interfere with potential new connection open on the same socket. So again, this is completely normal behavior. It does have a configurable timeout, and a lot of people would suggest here, hey, maybe you should like lower the timeout. I had this like issue before in my career, and there's usually a suggestion like that. But I think like with lowering the timeout, it's not actually addressing the underlying issue, and the underlying issue is that for whatever reason, the service is closing connections a lot. And writing high-performance services, you really want to keep the connections open as long as possible. Because opening them is expensive. So we used the netstat tool to take a look at the connections. We found the bug was one of our API clients that was basically disposing HTTP clients together with the connections. We fixed that. And also removed all the legacy outdated HTTP clients like the HTTP web request and the service point manager, and introduced HTTP client and HTTP client factory everywhere. These are the like new recommended ways of making HTTP calls in .NET. Decided, okay, this is the point we should migrate. On the right hand side, you can see like the graph after those fixes. Now we still have like some closed connections, but it's relatively low and expected. So we were happy with that. Second issue solved, making good progress. Here, like a short introduction, maybe you guys didn't hear about the HTTP client factory. So not only does it like properly disposes HTTP clients, it like pulls the message handlers. It has like this feature of respecting DNS changes. Provides like support for poly policies, which will be used later on in this presentation, and like allows to configure HTTP clients in like a centralized way with dependency injection integration, which is all nice. So we decided to use it and try it out. So solved second issue. Then we noticed like a third one, which was an unstable performance. For whatever reason, we were deploying the service, yet the CPU was behaving quite unstable. So at times it was like 30%, then you deploy again, the same version, it's 60, deploy again, starts as 30, goes up to 60. Wasn't very, very stable, very concerning. Didn't happen on Windows for whatever reason on the old version. So we decided to investigate. So if CPU is not doing stuff or doing too much stuff, it's nice to profile it. We use the perf profiler just because like we use it for other services that are not .NET. We just like it. It works for us very well. So important thing to remember is to enable the perf maps to be able to see like the symbols in those stacks. We recorded and a profile, we used flame grabs to visualize it and noticed that some parsing logic, if I remember correctly, or something like that, was having like a big Linko query, which took a long time, and under the hood it was a lot of equals operation, which pointed to default struct comparison, so value types when you compare them without implementing the proper comparison methods. The default comparison can be really heavy, uses reflection, not good. Funny thing is that we weren't using like a value type that we wrote ourselves. It was the key value pair from system collection generic. So I imagine whoever was writing it was like, the assumption was that it allows for comparisons, but apparently not. To avoid refactoring a lot of code, we implemented an I-equality comparer, which is nice because like instead of changing the value type or implementing your new one and refactoring everywhere, you can just inject it in like places where comparison is used and call it done. And on the right-hand side, now you have the graph after the deployment. And now everybody was getting very excited because you can see that not only is the Linux version is like 3 times faster than Windows, it's also like very stable. So basically like a flat line during the day, as opposed to Windows, which also has those ups and downs. Which was really nice. At this point, like everybody was okay, guys. Like tomorrow production time. Let's go. Let's take it. Let's claim victory. But we had other issues. So we felt kind of confident. We deployed more servers to production to start handling actual traffic. And at some point, they like all 3 of them basically crashed and burned and didn't wake up. So you can see that like the red line here is one of the Windows machines at the time was taking traffic. It wasn't taking as much because it wasn't as fast. So load balancer sends more traffic to faster machines. So Windows machines were getting like 30% more requests, but at some point they crashed and tried to wake up, and eventually they just died. Hinting at a deadlock or like lock contention, threadpool starvation, something like this. And good tools to analyze those is .NET Dump and .NET Stack. Basically allows you to check what the machine is doing, has like a bunch of nice features. The parallel stacks was good for us, but like if you've never used it, it's really easy now on Linux, and I highly recommend using it, even if you don't think you have issues, it shows you a lot. Unfortunately, it didn't show us anything, or at least like it probably did, but we didn't know where to look. We couldn't find the source of the issue. We found a lot of different things, but not the underlying source. So we resorted to other methods. So basically telemetry. We added a bunch of metrics, a bunch of logs, did code inspection, different metric inspection as well. We moved to async everywhere, which is actually harder than we thought, because those synchronous methods are hidden everywhere, and like I think this took us like, I don't know, 7 iterations to remove all that we found so far, and I bet that there's still like a synchronous call somewhere hidden in like a library that we consume or something like this. So we moved to async. We did like even synthetic load testing. We really tried to get a repro of the issue, but we couldn't get there. We basically like threw the kitchen sink at it. One thing was we noticed eventually was that at the moment of the crash, there was a spike of errors. Error spike is like the external cache that we're using, and right at the moment of the crash, there was a big spike of those logs, and this pointed to an issue with the client itself. And we found it. So basically, the client of the cache has a default mechanism. So the async max commands is basically max concurrency. So let's say you configure it to 100 requests. So at the time, you can only handle 100 requests to the cache. And if you exceed that, it's going to block the thread and just wait. This is the default behavior. It's very dangerous. Not sure why this for default. Like, you can do other stuff. We changed it to just reject, like don't make a call. But it was the thing that caused us to crash. And at this point, we decided, okay, we need to be more resilient to our integrations. We added Poly to most of them. Poly is like the resiliency library, the recommended resiliency library for .NET. Two of those nice policies we added was the circuit breaker. Basically, like if there's too many errors, you break, you stop making calls, and the bulkhead, which is again max concurrency. So we didn't trust the client to be able to handle like exceeding the limit. So we decided, okay, let's just not call it if we're hitting it. So we used those two and managed to resolve the issue. Unfortunately, well, right after that, we found another one. So we moved on. This time it was with HTTP client. Here on the left-hand side, there is a graph of CPU of our machine, which was like doing okay, below 20%. Eventually, like at some moment, it went down to like 10, 15. And we noticed on the left-hand side is the open connections, that it opened like 1 million connections, which is a lot, more than we expected by probably like 1 million. And then close them all at the same time and open another 1 million. Eventually, the app, we decided, okay, it's in an unhealthy state. We disconnected it from the load balancer. The CPU went to 0. And after that, it kept making HTTP connections for the next half an hour. So basically, the machine was not taking traffic. It was disconnected from load balancer, but next half an hour it opened over 400,000 HTTP connections, which is not ideal, which we decided to investigate and change. And this came to HTTP client implementation. So HTTP client, under the hood, it has a queue for requests and also a pool of connections. You can configure how many connections per server you want to open, and if there's more requests than available connections, it's going to queue them up. There are several things, like caveats here. One thing is that the timeout of those requests does not include DNS call. The DNS has a separate timeout. So first you make a DNS, the domain resolution, then only after that you start making the requests. The other caveat is that DNS calls in .NET 5 on Linux were synchronous. On Windows, they were async, but on Linux, .NET 5 had synchronous DNS calls, which we were surprised to learn. Also, CentOS doesn't have a default DNS cache. You can install one, obviously, but it doesn't come with one out of the box, which, again, like I didn't know. My bad. But so basically, every single request that came to our service was making a synchronous DNS call. And those timeouts were not included into the timeout of the request, which is not great. And there was a bug, an issue on HTTP client where it would still try to open a connection of a canceled request. So if the request timed out in the queue, it would still make a DNS connection, or try to resolve the DNS address and try to connect to the service, if I'm not mistaken. The issue was supposedly fixed in 6 .0. .NET 6.0.5. Haven't checked that. We worked around it, but this is basically what caused our service to be making so many calls even after we unplugged it. So our resolution here was first to move to .NET 6 because of asynchronous DNS. We decided that like we really don't want to be queuing requests. Like our latency needs to be below 200 milliseconds, and queuing makes it worse. So we introduced the Bulkhead policy from Poly to all of our HTTP clients. Bulkhead policy, this is the max concurrency basically. The default implementation of it logs a lot. So we need to implement our one ourselves with interlocked mechanism just to avoid locking, to not to eat that expensive locking operation. And on top of that, we added custom DNS resolver. We didn't want to rely on the OS cache and HTTP client to make DNS calls. We basically have like a very simple module running on a site resolving DNS addresses. All right, and this is what fixed it. Next time, or after fixing this, we got cocky. We decided, all right, we know what we're doing. We fixed like all those issues. DNS is now better. Everything's great. So now is the time to actually do some load testing. So we took a group of servers, not 3 anymore. It was like a whole, basically like a data center, although like it's a little bit more complicated. But and we decided to load test like a whole group of servers, a bunch of them basically. Here you can see the load test. We were unplugging them one by one, increasing the load on the rest of them. Basically, it's like sort of like chaos testing, but not really. And fun fact here, we kept 2 Windows machines just to compare them, and those are the 2 ones you can see right about here. So they were able to handle like about half of that what Linux did, until Linux couldn't handle anything anymore. As you can see, it like crashed quite a lot, and this was actually quite spectacular. So we were expecting trouble, and over here you can see us actually warming up some machines. So basically making sure that our caches are current and that we are able to handle requests if we need to. And we did need to, but it didn't help. So basically the machines crashed at some point and couldn't stand up anymore. Like they were flapping like healthy, unhealthy, healthy, unhealthy. So immediately we rushed in, we connected all the unplugged ones to the load balancer, but they started crashing as well immediately after connecting to the traffic, which is like a sign of a thundering herd problem. So basically load balancer, the system is so unstable that load balancer doesn't have enough healthy nodes to handle the traffic. And as soon as a node turns up and is healthy, it just crushes it with a flood of requests, killing it. Then another one comes in healthy, gets killed by load balancer again, another one. So basically, like without an intervention, likely this would last for a very long time. And what helped was those 2 Windows machines. So we kept them around. And at some point we decided, okay, like we are crashing right now. Our load balancer team is trying is like on their way to remove traffic from this group of servers to basically stop them from crashing. But we had like those 2 little Windows machines. We connected them back, and suddenly the whole system stabilized. And like we took a look at those logs, and those machines were taking like 100,000 requests per second each at some moment. Obviously, like failing handle anything, but they allowed us. They stayed healthy long enough to allow for our system to be stable. And like we didn't investigate a lot why, but like my understanding is that like the threadpool on Linux compared to Windows is a lot different, because Linux is doesn't have I/O completion ports and schedules I/O operations basically on the threadpool. So those two Windows machines came in handy, saved us from a bigger incident. So knowing what caused it and knowing how to avoid it, we decided to fix a bunch of stuff, mostly the load balancer configuration. We're running Nginx, so the max cons config value needed to be lower. So this is basically the max connections, active connections to an upstream server at the time. So basically like throttle the maximum number of requests that we're sending to each server. We made our connections keep alive for a longer period. So basically keep them as open as long as possible, not to like reconnect unnecessarily. We tuned our health check also to fail faster and check more often, basically. All this allows us to shed traffic in trouble and not try to kill machines trying to handle it. And one extra thing we experimented with was to slow start the upstream servers. So basically, when a server shows up to the pool, a new one, you don't send all of the requests right away. You allow it to warm up a little bit. So sending it like, I don't know, 20% of the traffic, 30, 40, and eventually 100. But this we decided, ended up implementing on the machine side, because on the machine side, we decided that we need to protect our precious servers from the evil load balancer. So we used IP tables to throttle the number of connection attempts that we allow. So basically, if we've got like 1,000 open connections that are healthy, that's okay. But if you try to open like more than 100 or more than 200, whatever the number is, it's gonna reject like the overflowing connection attempts, basically. So this setting is basically what allowed us to not see thundering herd again. Not sure if this is like a common practice, but yeah, basically we are blocking load balancer from opening too many connections at once. Worked wonders. We never saw it again. One important thing to notice here is that you really want to whitelist health check. Like you don't want health check connections to be throttled by IP tables, because then the machine will show us unhealthy and start flapping as well. So this was a big issue that we fixed, but wasn't the last one. Again, we saw a sign of a deadlock or lock contention / threadpool starvation. So here we were more careful. We didn't do like full load testing. We just like ran a bunch of nodes with higher number of requests, and at some point they all failed at the same time. Other nodes, like this is a sample of them, other nodes were able to handle them just fine and pick up the load that the machines were dropping. So again, we needed to investigate. And this time it was the circuit breaker from Poly. So we discovered that by accident, actually. We were like, again, looking everywhere, not seeing signs of anything in memory dumps, not seeing signs of anything in CPU profiles or any other tool. So we were investigating like different policies and eventually discovered that removing circuit breaker actually made our service a lot safer and reliable. Circuit breaker in general worked okay, but when it's breaking the circle, the implementation in polylib, it's actually locking, and in our case, that locking caused those lock contentions, basically. So at this point, we decided to remove poly altogether, just for having like too many issues with it. The original Bulkhead implementation locks, circuit breaker locks, and the policy wrap caused our CPU profiles to be tangled up. So basically, like we couldn't really use flame graphs properly, because like policy wrap for whatever reason just messes up with async continuations and doesn't present like the stacks in a nice way. And the new version, after removing the circuit breaker, had 50% bigger throughput, 200 times less errors, 20 times less reconnects, less CPU used on those high loads. We basically went from 25,000 requests per second to almost 40, like 38, 39,000. And this is like at this point we like realized that like the very first version of the service was actually designed to handle like 40,000 requests per second, and now we were able to handle it on just like one machine, which was really something. We were really happy about that, and we ended up at this point only using our own implementation of Bulkhead without the circuit breaker, which worked for a while until it didn't. So this time, again, HTTP client issues, but not really. Like this was caused by an external integration having timeouts. So on the left-hand side, you can see request per server. And at like a peak traffic at night, we were getting like drops of like 50% of the requests and active open. So basically our server opening new connections was spiking into like 1400 per second or something like that. And we were basically timing out, opening a bunch of new connections, timing out again, a vicious cycle. So obviously we realized that like the max connections per server in our case is not enough, because we are making a lot of HTTP 1.1 connections. So each of our requests needs to have its own connection. And in case there are timeouts and we are handling like thousands, tens of thousands of requests per second, we are opening just too many of them, basically, not something that the machine can handle. Circuit breaker pattern for us, like it was too binary to begin with. Like it's either healthy or unhealthy. The circuit is either open or closed. So it doesn't really help us here where we really want to slow start the connection. So basically like open a pool of them and then we can actually handle a bigger load. In our observations showed that like here on the right-hand side on the bottom graph, you can see like the threadpool queue length was actually like growing to like thousands of items in the threadpool queue, meaning that threadpool was having also issues handling all the work, and threadpool stalls and timeouts cause actual timeouts, which then those contribute to threadpool stalls again, which wasn't really nice. So similarly to our thundering head problem, where we were throttling the number of connections opened by the load balancer, now we needed to find a way to limit the amount of connections that we are opening by HTTP client. First approach was to use the connect callback. So basically HTTP client allows you to implement your own method of opening a new socket, and in there we injected a bulkhead policy, so max concurrency, that only allowed to open, I don't know, n number of connections at a time. So we were like experimenting with like some very strict policies that only allows to open like, I don't know, 20 connections at a time, 100, and this actually helped a lot. But it was also like throwing exceptions and handling overflow by throwing exceptions, which is not great, because throwing exceptions in general is kind of heavy, is a heavy operation. So we couldn't like do that in the long run. So what we ended up doing is creating a new custom resiliency policy, which is basically an adjustable bulkhead, adjustable max concurrency. So it only allows you to, it's tailor fit to handle connection pools and only allowing you to open X amount of connections at a time, but allowing you to use the existing open connections. So basically this policy is trying to track how many connections the HTTP client has open, use those, and only allowed to open X number of new ones. And we, like, the first version of it like saved our system over like a bunch of nights. Basically, like over the weekend we deployed the Canary version of it, and it was good enough for like the Canary servers. On the right hand side you can see like the green server is the Canary, and like the rest of the servers, like you've got 3 servers here, but the rest were failing, and all the canaries that were running, like the new version of the code, were able to pick up those requests that the rest of the servers were unable to process. So the first version worked very well. We actually are using it now not only for HTTP clients, but for all of our integrations. We're hoping to open source it as well, because it's like very niche, but also worked very well, relatively simple as well. One thing we noticed here that we cannot fail too fast. So when those timeouts happen, when you're like rejecting integration calls because of resiliency policy, you really don't want to do it like right away, because then your service, let's say the service is failing for whatever reason, cannot make any HTTP calls, rejecting all of them. Suddenly it becomes very fast, and load balancer sees that and starts sending it a lot of requests. And this creates basically a sink for requests to get wasted, because like unhealthy server is failing too fast and then hiding it from the load balancer. So we added a delay after the policy rejects an item, a request. We wait for the average latency of the integration call, which allows us to not to trick load balancer to send us more traffic. And one more thing we added to keep those connections open for a longer time, because we noticed that threadpool issues caused us to close them, is to extend the timeout on those connections. So our SLA hasn't changed. So what we ended up doing is we added a separate timer for those requests. So after that timer expires, we just assume that HTTP call will return nothing, and we move on processing the request. But in the background, the HTTP client has a higher timeout, and it's still processing the call and still keeping the connection open, allowing it to, keeping it open for a longer time, not closing it preemptively because of our high SLAs and threadpool issues, basically. We basically discovered that most of our timeouts were actually caused by threadpool issues and not actual timeouts of our backend services. So one thing to mention here, that there is a timer queue in .NET, and if you end up creating too many of them, like this could cause an issue. And we did notice that we are creating a lot of them right now, but so far it's been okay, and we create like thousands of timers. We have a metric for it, and try to take a look at it every so often to make sure that we're not abusing it too much. And this is the last issue that we solved. This is the very simple one. We noticed that even though we implemented all those policies, we have like nice timeouts now and whatnot, our servers were closing connections in a very regular cadence, and turns out it was the HTTP client factory. As I mentioned before, it has a piece of logic that allows to handle the DNS changes. So basically what it does is has a handler lifetime, and after the lifetime, it closes the handler and closes all the connections and opens new ones. So it's like the default, I think it's in 2 minutes. So basically every 2 minutes, all of our servers were closing all of their connections and opening new ones. We noticed this. Well, this is not a lot of connections. Like it was mostly okay, but one of our clients is actually sending us requests in bursts, like every minute. And sometimes there were times where like servers synchronized, like the HTTP client factory was closing the connection the moment the client was sending us a burst of traffic, which is not great. We ended up not using HTTP client factory anymore. Like we don't really mind singlet on HTTP clients. We resolve our DNS with a custom resolver anyhow. We're not using poly anymore, and the dependency injection integration is not super helpful with singletons, which we are using not to allocate too much. So even though it's recommended, both HTTP client factory and poly, like we ended up not using any of them. So final results. We no more have scaling issues. Our service scales very well. We use 50% less electricity while having 3 times the throughput. We were able to switch to newer, more energy efficient hardware and utilize it to its fullest potential, or as close as we could get. So big savings on hardware and no more midnight pages, because the service has awesome resiliency policies and is very, very stable right now. A couple of lessons learned. One thing was to optimize the right thing. We had a lot of people on the way asking us, like, have you guys looked at flame graphs? Maybe flame graphs would tell us, like, in our case, our service is very IO bound. We're making a lot of HTTP calls, waiting for the results. Like, the most important thing for our service is to be able to juggle different requests very well and to switch between tasks in a smooth way, to not to wait on synchronous calls. And flame graphs help, but I think .NET dump was the tool for us to use to analyze what threads are doing. Basically, .NET dump, .NET stack, and finding those synchronous calls and getting rid of them. The other thing is, like, don't put off fixing known issues. Like, most of those issues, big part of those issues we were seeing signs of to begin with, but we were like focused only on the main issue at hand and like pushing everything for later. So like DNS thing, we noticed like right away, but we ended up like fixing it as a third or fourth issue. So like if you notice it and it like feels like trouble, you should probably just address it and fix it and not wait for it to bite you again. Don't be afraid to implement your own stuff. So in our case, we used Poly to begin with, like trusting it, but like I'm not saying Poly is bad, but in a really high performance environment where you really don't want to log so much, consistency is not the key. Like you really need a fast policy and not one that logs. Going full async is not very easy. I mentioned before, like finding all those synchronous calls made by some NuGet packages that you are using is quite difficult, more difficult than we thought. We kept finding it like over and over again. Big lesson here, the biggest one would be like, don't rush to change the OS, like migrate to .NET 6 first and then like have it running on the same like Windows and then only then switch to Linux, because a lot of the issues that we've seen were caused not by the difference in framework, they were caused by difference in the OS. And the last part is like be patient. I think from the time that we first had like asks from like the business side, like when are we ready, when the migration is happening, to the time I was actually happy with the service, it was like almost a year. We migrated like sometime in the middle, but be patient. Like don't rush it. It's gonna crash on you if you do. And that's it. That's my presentation. I hope you guys enjoyed it. Hope you guys learned something. I know I did.
A lot of lessons learned, indeed. You have your camera stalled. I was not interrupting you, but you have frozen in a... Yeah, maybe you can restart it or whatever. Maybe I will try to take you out of the stream for a second and come back. Just as, if something is not working, we should restart it. So let's just try that.
Sure.
And no, but do we hear each other?
I can hear it quite well. Yes.
Okay, let's just stick with this configuration then. So unfortunately, people will see the black screen instead of your face. Just not to prolong the question, to prolong the session. We have one question from chat as far as I'm seeing. So let's see. I have a driver leaking memory, but I don't know what it is. What would you recommend to find out which driver is leaking memory? It is as Jose, it is not .NET driver, right? Probably.
Yeah, if it's not .NET, you should probably like take a look at different profilers for the OS that you're running on, or the driver itself. Like .NET tools will not help you there. Some of the integrations that we've used, they used unmanaged code as well, like some C libraries, and .NET tools are not really good at great at analyzing those as well.
Definitely, unfortunately. Every operating system have bunch of tools for tracking memory, right? Performance monitor in Windows, even task manager on Windows, HTOP or anything else in Linux. So unfortunately, you will need to learn them. Jose, no good answer for this. And let's give very last minute for questions. If you have any, do not hesitate to ask. I have one. When do you plan to migrate to .NET 7?
I was actually hoping to have a demo of it, at least like migrate one server for this talk. We haven't had the time, but as soon as it comes out, basically, like we try to adopt it as soon as it's out,
Awesome.
which I believe it's November.
So you are not waiting for LTS version .NET 8?
No.
But I hope I hope you will not find much more issues. Although then you could make another session, or at least extend this one. So fingers crossed for migration to .NET 7. Okay, we don't see any more questions. So from our side, it's all. Thank you very much for being with us. Sorry that we are not seeing your face. Something has gone wrong, but at least at the very end. And I was enjoying this talk a lot. I hope you enjoyed it too. I hope you all enjoyed our conference. So thank you again for sponsoring this conference. Thank you all speakers for being with us, and mostly also thank you for to all attendees for being with us. So although it is online, we haven't seen each other. We had some kind of interaction on chat, on Discord. So thank you very much for being with us. Thank you, Krzysiek, and thank you all to
thank you. Pleasure.
all the speakers. See you somewhere next year. This year we will see where. I hope we will meet. Thank you very much. Let's take a rest. Thank you. Bye.
Bye-bye.